Hello, everyone. So I guess it's a good afternoon for me because right now I'm in Beijing, China right now. I'm a PhD student in Tsinghua University. So today my talk is a dynamic model for ride matching problem in multi-hop ride sharing system. So first, I think it is important to do some introduction about multi-hop ride sharing. So ride sharing, as we all know, is just like taxi or a bus is one driver carrying multiple riders with different ODs. And multi-hop means so the trip of riders can be transferred among different drivers. So these two factors combined makes the multi-hop ride sharing scenario. So the multi-hop ride sharing scenario can also be referred as many-to-many ride sharing system. So there is a tremendous amount of study about the ride sharing system, but not so much about multi-hop ride sharing system. I think the major reason for that is a complicated model, and the complexity of this model happens during the matching phase, the rider and driver matching phase in the system. So I think the major two major points of all the complexity can summed up as a first breaking up passengers trips to sub trips, and second is to iteratively combine the sub trips to vehicle routes. So the emphasis of this study is to break down the complexity itself, and we tried to describe the complexity with a model and give a feasible solution to this complicated model. So in the problem definition, so yeah, let's start with some parameter definitions. So this is a pretty straightforward. You can find a similar definition in many different studies. And in this study, so we wanted to use time as a parameter more often. So we adopted the assumption that passengers will deliver their preferences for time of departure and time of arrival. So this is a popular assumption used in the mobility on demand type of study. So I think using this assumption can put time as a controlling variable more often in the study. And also we adopted the assumption that passenger will deliver their preferences in the ride hailing system. For example, like whether to accept their ride to be shared or transferred. So we have three sets of parameter defined. For example, so there are passenger info, passenger records, and vehicle records. So one interesting thing is after the introduction of this assumption, so of these two different time, we can introduce a new one, a new parameter. So we named it as abundant time. So the abundant time means the difference between the time of latest arrival and predicted arrival. So to clear the ambiguity, so let's refer to this graph. So it's a graph of a time expanded network. This is also a straightforward definition. So in in common network, we will define nodes and edge in a common sense way. But in this in time expanded network, we will define network with time. So a dynamic network will become static network in the time expanded network scenario. So it will put time to a better use. So as you can see, the right line here represents a shortest route of a vehicle, and the red, so the area, the region enclosed by red color represents the place the vehicle can go during as a detour, So this area actually represents the abandoned time. So within the abandoned time, the vehicle can serve to these places without violating their original tasks. So actually, the abandoned time represents the time budget of detour. So let's go back to the definition here. So abandoned time means a difference between time of latest arrival and the predicted arrival. So it's actually a budget of detour. And so as I mentioned in the first slides, so the emphasis of this study is the matching phase of the system. And actually the matching phase can be represented by the intersection of the abandoned region of vehicle and passengers. So the red area, the red region is still the region for vehicle, and the blue region is the abandoned region for a passenger. So if you want a successful match between the vehicle and the passenger, you only need to find the intersection of their abandoned region, because the intersection of their region means they all both the vehicle and the passenger have the luxury to detour a little bit to accommodate the route plan of their counterpart. So which becomes the green line. The green line means the new route for the vehicle to pick up the blue passenger. So so the intersection became the matching area. And how about so we also need some objective function to optimize the matching process to just to try to find the right size or the right location of the matching region. So here I define 4 different objective functions with the same dimension. The dimension used here is time multiplied by distance. So the first one is to make sure the vehicle and the passenger share similar direction. Their routes have share the similar direction, and to be close to each other as much as possible. And the second one is to minimize the vehicle's deadheading and the waste of the abandoned time. And the third one is to make sure to minimize the extension of vehicles' routes, both on the level of time and the distance. And the fourth one is to minimize the extension of passengers' routes. So after we clear the logic of how to use the the matching the matching process, one of the important point of this model is to how to locate the matching region. So I got this idea from the study of Professor Masood in this literature. So the Professor Masood invented a method called reduced network, which means if you draw an ellipse of the, for example, a vehicle, for example, a passenger in blue, and the OD as the focal point of the ellipse. So this ellipse area will actually enclose the best route for the passenger. And also, so the same goes with the intersection of vehicle and the passenger. So the green area is the ellipse area for the vehicle. So so as you can see, the best route for the match here is 5, 6, 7, and 8, and 12 for a passenger to go from 5 to 12. And I developed this method a little bit into a 3D dimensional case. So an ellipse became an ellipsoid. So so the x or y plane is the original planar network, and the z-axis here represents the extended time. So so we can also represent the passengers ellipsoid ellipsoid region as this, and the and use it to intersect with vehicles ellipsoid region. So their intersection, for example, if we want to find a certain vehicle at time t, so we only need to intersect the ellipsoid with a planar defined by z equals to t, and so the intersected area is also an ellipse. So the ellipse can and we can use the Tracy tool in Sumo platform to locate the vehicle we want, and thus go further on the matching process. So so how should we define the ellipsoid? So it's pretty straightforward, and we only need to rotate the ellipsoid a little bit by beta, by the degree of beta, and introduce the time limit and the time limit into this equation. And this equation actually introduced another interesting parameter. So it's k equals to time limit to time short, which so the time limit here is the time of latest arrival, and time short is actually the time of predicted arrival. So that goes back to the definition of abundant time. So k is the became the detour ratio of this match. So after we reintroduce the k into the original equation, so we can after some calculation, we can have the midpoint of the intersected ellipse focal point DC. So we which actually is the midpoint of this ellipse, and we can use a real quick analytical solution in this case to find the long and short length, long and short axis length. So after we have the midpoint and the short length of the length of the short axis of the ellipse, then we can use Tracy to find the to locate the vehicle we needed for the matching process. So this is the program I wrote. So so that is a major program, and I used Sumo as a basic platform and Tracy as the control unit to control vehicle behavior here. And I used the libsumo to dissect the network and Tracy to calculate the shortest route and shortest time, etc. So for the experiment, I used data from DD ride-hailing trip. So basically, it's a taxi data collected in Haikou City, China. And I selected only 1 hour of the data set. And this is the vehicle setting in the experiment. And for so I ran 2 different experiments. For the first one, I first defined a calibration group, try to make the simulation as close as to the real scenario. And the first group of the experiment 1 is 1 to 5. I will refer to them to experiment 1.1 and to 1.5. So that so the fleet size will be 119, and trip requests, the number of trip requests will be 1,064. So that's actually 1/4 of the real capacity of the data set. And for the second group, I doubled the trip request in 1 hour, try to put the system into a pressure test and to show the capability of the ride sharing system. And for the experiment 2, so I also doubled the trip request and set the value of k, which is a detour ratio, in the following number. So that is actually the maximum value of value k allowed in the system. So the point of setting the maximum value of value k is to limit the search area. Is to limit the search area of the intersection. So if we set a smaller value of the detour ratio, so the software will search less in the matching phase, which gives us a poor solution, but a faster solution. So the value of k I used in this study is from 1.1 to 2.0. So the result for the experiment 1 is shown in this page. So for the first group, which is a normal case, as you can see, in the left figure, so the left graph grouped all travel requests by the reserved departure time, and the right graph grouped requests by their traveled distance, and the y-axis is the same as the travel time delay. And the left graph shows that the later trip request might suffer from a lack of vehicles, which require them to wait longer. So the travel time delay goes up, and the drop of delay in this group shows that some vehicle could have finished their previous trip orders and replenish the taxi fleet. So although with some fluctuations, you may see that experiment 1.4 and 1.5 here. So for 1.5 and 1.4 and 1.5, so I set the ride sharing acceptance and transfer acceptance as 50% and 100%. So experiment 1.4 and 1.5 show a quicker recovery from the delay. So 1.4 is the purple one, 1.5 is the orange one. They recover better from the delay, and which indicates that adding in transfers, a higher ratio of transfer and ride sharing could help the system recover quicker from the lack of taxis by integrating trip requests. So the right graph shows that experiment 1.4 here, the purple one, and 1.5, the orange one, perform better when the trip distance is less than 6 kilometers. It indicates that longer trips requires higher exclusiveness from vehicles because the longer the trip, the fewer the passengers share similar OD points. Thus, ride sharing and transfers can hardly perform for longer trips. And judging from these two graphs, experiment 1.5 show better performance than other groups, the orange one, and for most of the time, yes. So I think the multi-hop ride sharing mechanism has shown that it could provide some better performance than the solely use of ride sharing or the transform mechanism. So the solely use of ride sharing is this group, the 1.3, with only 50% acceptance of ride sharing and 0 acceptance of transfer ratio of ride transfer. And the same goes to the group of experiment 1.2.
Excuse me, you have 1 minute left.
Sorry. Okay, I will just finish with this graph. Okay, so showing in this graph, a total travel distance, the blue one, goes down while the infiltration rate of the ride sharing mechanism goes up here. And by comparing the result of 1.4 and 1.3, although have not been proven, it's highly possible that adding in transfer helps the ride sharing mechanism perform better for total travel distance. And the total travel distance with passengers, the green one, are dropping and save the distance increasing. That's all. Thank you.